Hello and welcome to part one of topic two of the Year 11 Software Design and Development course. Today we're going to be looking at hardware and what do we need to know about how hardware works in a computer system from a software developer's point of view. So I often get asked, why do we as software developers need to study hardware? Well, it's useful to know how our programs are going to be interpreted. It allows us to then build more efficient and more reliable software because we'll have a better understanding of how the software and the hardware relate to each other and how one runs the other. We're going to look at the different types of hardware. So we're going to have 4 or 5 different groups of hardware. We're going to look at input hardware, output hardware, how things are stored, processed, and what controls the system. So when we talk about input hardware, we're looking at anything that puts data into the system. Okay, now for a computer system to be of any use, it has to be able to accept input from some source. And these different types of input can be quite varied and very different. So we've got the ones that are pretty obvious. Keyboard, mouse, that makes a lot of sense. But we also have microphones, cameras, any kind of sensor like temperature or barometric pressure, optical like a camera, motion sensors, any files or databases, even our networking devices are putting things into the system and thus considered input. For a system to also be useful, we have to have output. So once we've processed data, we need to output the result of this. And this has been done in several ways. The most obvious, of course, is screens. You're looking at one right now. But also printers, networks, and actuators, or what robots use to move around, can be considered types of output device. Storage is also a bit integral part of the system because we'll often need to store the results of any kind of computation or processing of data. And it's the ability to store and retrieve information which makes computers so very adaptable and useful to us. There are 4 types of data, and they kind of combine to make different sort of data sources. We've got primary, secondary, permanent, and temporary. So we can have primary permanent, primary temporary, we can have secondary permanent and secondary temporary. Types of storage. So the 2 main types that we're going to talk about are primary storage and secondary storage. Primary storage works closely with the processing system, CPU and everything else, and for the most part requires power to retain its information. So your RAM, for example, which stores all of the programs and all of the data that you're using while you're actually running the computer, you turn the power off, it's all gone. The only exception to this is ROM, or read-only memory. This doesn't require power to retain its data, but then again, you don't write to this, at least not very often. So this would be your boot system, for example, or your BIOS. So it's the hard-coded operating system that allows the computer to load the operating system that you'll use into RAM. Secondary storage is usually greater in capacity and doesn't require power to retain its data. So that's your external hard drives or internal hard drives, even CDs, DVDs, Blu-rays, things like that. So let's focus on primary storage. This is often referred to as main memory or just memory. We don't usually talk about it as primary storage. Storage most people think of as your hard drives and secondary storage. So when I refer to memory, I'm referring to primary storage. In your CPU, this will include RAM, the CPU, primary storage itself, any caches that you might have, ROM, and virtual memory. Except for ROM, main memory is volatile. Okay, now when we say that something is volatile, it means that it has to have power and it's data that is not used to store permanent information, merely process it. So we don't actually care about saving long-term anything that is in volatile memory. ROM is, like I said before, is information that is very rarely, if ever, changed. And this would be your startup chips and bootstrapping. When we talk about secondary storage is used to store data in a permanent way. This is something that has been rapidly expanding. It's actually changed quite a bit in the last 10 years. So in the last probably 20 or 30 years, there's been exponential growth in the amount that you can store and also a decline in price until recently, which is quite interesting. So I did some research on the average cost of secondary storage. So in 1956, you could buy a 5 megabyte hard drive. And it would cost you $50,000, which is $10,000 per megabyte, when the average weekly wage was around $65 in the US. It was the size of half a fridge, a stove, dishwasher, about that size, and very, very heavy and would have to be specially ordered and made for you and all the rest of it. 1980, we got up to 26 megabytes, 1987, 40 megabytes. And these are starting to be sort of things that you could take home or have in the office. By 1995, 2.9 gigabytes, how exciting. Still cost you $2,000 or $3,000, but you were down to about $1 per megabyte. After the year 2000, and you can see here that we've switched to cost per gigabyte, we finally start seeing we're getting into the hundreds of gigabytes and then ultimately into the terabytes. The last year that I did do recent research on the price, and the thing is, the prices have actually gone up, even slightly more than inflation for 8 terabyte drives. I think this is probably due to a lack of demand, as more and more people are storing everything in the cloud, which is again a different type of secondary storage. Now, there is kind of like a weird thing about this course where we need to talk about things that no longer exist. People often sort of immediately assume that I'm talking about magnetic tape. Actually, magnetic tape is still used quite a bit. It is super, super cheap. It is used for backups when you think you're never going to need it, but just in case. In fact, even Amazon will provide magnetic tape backups on their Amazon Web Services. It's called Glacier, which is a comment on how slow it is. It's also sequential, which means that if you are looking for a file that's at the end of the tape, you'll need to read in the entire tape to get to it. Hard drives we've looked at. We've also got, back in the day, we'd use these things called zip disks or super disks. They were small cartridges, very expensive, but they were about 100, 200 megabytes. It got up to about a gig at one point. But like I said, they were like $200-300 per disk. Floppy disks were small, cheap, portable, but had very limited storage. You could still probably, if you rummage around in sort of like the bottom of drawers of old desks, you'll find these all over the place. Even up to about 10 years ago, it was super common to have CDs and DVDs floating around everywhere, and you could write to those. But now they're largely gone and forgotten about. Flash drives still exist because of their ubiquity and easiness to use, and they're actually starting to develop some large capacity. But again, with everything being stored in the cloud, the days of secondary storage are probably limited. Okay, so we've got a computer. How are we going to actually use it? How does software run on it? So we've got a central processing unit, or CPU. You're familiar with the term CPU. And most computers these days will have multiple CPUs. Modern computers largely follow the design of a guy called John von Neumann. He created the ENIAC computer in the 1940s. It was a very important step because he broke up the computer into different sections. And so you'd have a different section for logic gates, you have a different section for multiplication, you have a different section for adding files, things like that. So, well, not that they added files, but he'd have different sections for doing different parts of the work of the CPU. And this is still pretty much the way that we build computers these days as well. So in the CPU, we'll have registers, the arithmetic logic unit, which essentially is exactly what it is. It does all the math. We refer to it as the ALU. We have a control unit, which contains the system clock and buses to transfer information around the computer. Here's a look at the ENIAC. In the early days, majority of programmers were actually women. So they would take the formulas that were created by the men who didn't know how to program, and then they would implement it into the actual machine. You can see here that they're programming by using cables. You can see more transistors. These would blow up fairly frequently and have to be replaced. Okay, so registers are a special part of the CPU that store data and instructions that are currently being used. They're not a part of memory, but are a part of storage. They work in conjunction with CPU. They store and process instructions in a temporary fashion. There are 4 types of register that you need to be aware of. The accumulator, which stores the results of computations. The address register, which stores the memory location of the data as it's being processed. Storage register, which is a placeholder, and any general purpose register, which is used for anything else that you might need to use it for. The ALU is special. It compromises several different circuits, and it do 3 or 4 different things that are kind of important. Arithmetic functions, addition, subtraction, multiplication, and division. Logical functions, so this is your and, or, not functions. And they compare numbers greater than, less than, equal to. The control unit synchronizes the whole thing into place. It decides which tasks are going to be used, when we're going to do them, and what paths are going to be used. The system clock keeps everything in sync because remember we've got a lot of computers doing different things, or different parts of the computer doing different things. So the system clock needs to sort of keep everything in order, otherwise we're processing the wrong data. Buses are used as pathways to send information to the different components within the system. All of this happens as part of the fetch executed cycle. So CPU executes only machine code. Okay, so machine code is binary or assembly. The CPU executes instructions in a set order. The cycle is broken up into instruction time and execute time. So what instructions we're going to use, and then we're going to execute the instructions. So we fetch the program. So we've got a counter that points to the instruction to be executed. We decode that. The control unit takes the instruction, decodes it, sends it to the appropriate registers. The CPU, or the ALU, executes those instructions, and then they store the results into memory. The whole thing looks like this when we put it together, or more easier to understand, this. So here you can see we've got the instruction fetcher, which fetches the code, we decodes it, we execute it using the ALU and registers, and then we store in memory interface or send it to secondary memory. To remember the fetch execute cycle, fall down every stair. FDES, fall down every stair, fetch, decode, execute, store.